Good morning. We are Andy Clements and Cora Clements for our csc372 Learn a New Programming Language project. We chose the programming language Go. For part 2, we wrote a required PGM image threshold program, and for part 3, we wrote a Htop-lite terminal-based system monitor inspired by Htop. In this demo, we will run our part 2 image program, and then we'll demonstrate our Htop-lite and explain how it goes through Go's strengths, especially Go routines, channels, packages, structs, and clean concurrent design.
For part 2, the program accepts a PGM image on the command line, computes a global threshold, and writes a black and white PBM image with the same base file name. The algorithm starts from an initial threshold based on randomly selected pixels, repeatedly partitions pixels below and above the threshold, recomputes the means, and stops when the value stabilizes and reaches the iteration limit. This helped us learn Go's file handling, command line arguments, slices, loops, and error checking. We are running the program on the required sample image desertclouds.pgm. The output is a PBM file, which is the black and white segmented version of the original grayscale PGM image. The dark pixels represent the group below the final threshold, and the white pixels represent the group above or equal to the threshold.
For part 3, we wanted to build something that fit Go instead of just writing a simple sequential program. Go is known for simple syntax, fast compiled programs, and especially built-in support for concurrency. A terminal system monitor is a good fit because several things need to happen at the same time: CPU data collection, memory data collection, process scanning, network monitoring, keyboard input, state updates, and screen rendering. The project is organized into packages. The main package starts with the program, creates the channels, launches the Go routines, and handles the shutdown. The collector package contains the CPU, memory, process, and network files, which each gather one type of system information. The events package defines the input event package to use for keyboard actions, and the state package contains the manager, which combines all the collector data and input events into one system state. Finally, the UI package renders it all to the screen. This design creates on the main.go program. This design here creates a pipeline. The collectors send typed snapshots through the channels. The state manager receives those snapshots, applies filtering, sorting, and scrolling, and selection logic, and then sends a complete system state to the renderer. The renderer owns standard out and redraws the terminal UI. That separation keeps the program easier to reason about because each package has a clear job.
Now we will be running the Htop-lite. At the top of the program displays the overall CPU usage and once per core CPU bars are located. Under that, it displays memory usage and network upload and download rates. The main table shows running processes with PID, name, CPU, percentage, and memory used. The display updates about once per second, while the collectors continue running in the background. The process list is scrollable. The input handler reads raw key presses, converts them into input events, and sends those events to the state manager. The state manager updates the selected processes, scroll offset, and then the renderer redraws the table with the selected process highlighted. The S key cycles through sorting modules. The state manager stores the current sort field and sorts the display processes list by the CPU usage, memory usage, PID, or process name. This is a nice example of Go's simple enum-style constraints using iota and standard sort.slice function, with the inline comparison functions as well. The slash key enters filter mode. In filter mode, normal printable characters are treated as search text instead of command. The input handler sends the current filter strings to the state manager, and the state manager rebuilds the process list by matching process names, case, and sensitivity. This shows a clean, event-driven design. Input does not directly change the UI, it sends a message, and the state manager updates the state. The program also supports a kill action with X. We are not going to kill important processes during the demo, but the implementation gets the selected process info and kills the method. That method asks the operating system to signal the selected process while logging success or failure. This feature is intentionally careful because operating system permissions can prevent killing some processes.
The most important Go feature this project demonstrates is concurrency. In main.go, each collector, the input handler, the state manager, and the renderer are started as Go routines. They are lightweight concurrent functions managed by the Go runtime. Instead of sharing global variables, the program communicates through channels. For example, the CPU collector sends CPU snapshot structs through the CPU channel. The memory collector sends memory snapshots or structs values through the memory channel, and the state manager combines them all together. Program also uses context cancellation for a clean shutdown. When the user presses Q or Control C, cancel is called through system calls. Each go routine checks the context.done and exits cleanly. The main function uses a wait group, so it all waits for all the go routines to finish before the whole program finishes. This is the kind of coordination Go is designed to make approachable. Another interesting design choice is that the collector channels are buffered with size 1, and the send or drop functions replace the stale data with the newest snapshot. For a system monitor, old CPU or network readings are not useful. We care about the latest value. This makes the program responsive and prevents from slow rendering and a buildup of backlog of the old frames. For style and documentation, we documented the main program and the important packages. The main file explains the purpose of the program, the external packages used, and the channel setup, the go routines, the signal handling, and the graceful shutdown. The state manager documentation explains sorting, filtering, scrolling, select process logic, and broadcasting state. The collector files document how each system metric is sampled and sent through the channels. We also documented the shared data types and the input events. This matters because the program has multiple moving parts. Good documentation makes it clear whether each channel carries what each struct represents and which package owns which responsibility. That is especially important in a concurrent program where unclear ownership can make code hard to debug.
What makes this project interesting to us is that it is not just a basic syntax exercise. It is a real-time terminal application with multiple concurrent workers, typed data snapshots, keyboard input, terminal raw mode, ANSI rendering, sorting, filtering, and operating system interaction. We learned how Go's simple syntax supports a fairly complex architecture without needing heavy frameworks. We also learned that terminal programs need careful cleanup. The input handler puts the terminal into raw mode, and the renderer hides the cursor. On shutdown, the program restores the terminal and logs each go routine stopping. That makes this program feel more polished and reliable. In summary, our language was Go. Our Part 2 program demonstrated the image threshold from PGM to PBM, and our Part 3's program is Htop-lite, a concurrent terminal system monitor. We chose this project because it uses Go's strengths directly: go routines, channels, simple struct, standard library coordination tools, and fast compiled execution. After recording, we will upload this video to Google Drive or YouTube and include the shareable link in the README for Part 3 submission.